Since the first astronomers pointed telescopes at the heavens, they have sought to see more, see farther, see deeper. Space astronomy changed on April 24, 1990, with the launch of the Space Shuttle Discovery, carrying aboard it the Hubble Space Telescope. A lot of people think we launched Hubble into space to put it closer to the stars, but the real reason lies in that old children's song, Twinkle, Twinkle, Little Star. We all know that song, and it describes a very real phenomenon. The Earth's atmosphere both distorts and blocks light coming in from space. In space, beyond the atmosphere, the stars don't twinkle. They shine steady, and that allows you to get the stunning images we've become accustomed to seeing from Hubble. But that wasn't Hubble's only benefit. It's also one of NASA's great observatories. These are general-purpose telescopes designed to be able to observe anything and everything in the cosmos. There are a lot of observatories in space, but most of them are designed to answer one or two specific questions. Hubble was built to be as inclusive as possible. It was supposed to answer as many questions as you could think to ask, at least as far as its design allowed. And Hubble succeeded splendidly at that. We've seen planet-wide dust storms on Mars. We've seen the astonishingly strong and surprisingly variable auroras of Saturn. We've looked deep into dense star clusters containing tens of thousands to millions of stars. We've examined the birth of these clusters as they emerge from the interstellar clouds. And we've watched stars die, some releasing their outer layers gently into space, like smoke rings. Others forming cosmic butterflies. Some expiring in tremendous explosions that blast their material across the cosmos, expanding for tens of thousands of light years until their remnants ultimately fade away. We've explored the varieties of galaxies, some with beautiful spiral shapes, and some with vast ellipsoidal collections of hundreds of billions of stars. And we've seen galaxies in massive clusters of thousands arrayed through space and time. This is perhaps the most important image Hubble has ever taken, the Hubble Ultra Deep Field. It shows us galaxies stretched all the way across the universe, 5, 6, 10 billion light years away. This is light that's taken billions of years to reach us in our corner of the universe. So we see these galaxies not as they are today, but as they were when the light left them, like getting a postcard in the mail that's been traveling for a very, very long time. And in the end, we see nothing. Is that because we've reached the end of the universe? No. What we've reached is the limit of Hubble's vision. As amazing as Hubble has been, we've come up against the immutable reality that Hubble can't, in fact, see everything. To carry us farther, to step beyond Hubble, we need the James Webb Space Telescope. Like Hubble, Webb is a general-purpose observatory. And like Hubble, Webb will orbit in space, giving it the clarity that comes from being beyond Earth's atmosphere. The Webb telescope sees infrared light, which is visible to the human eye, though we still perceive it as heat. Putting an infrared telescope like Webb in space is going to open entirely new regions of the universe to us. To understand this, you need a little astronomical background. You've probably all heard that our universe is expanding. But what you may not know is that as it expands, the light traveling through the universe also gets stretched. So what started out as visible light and ultraviolet light, the two types of light the earliest objects in the universe emitted most strongly, is changed. It's stretched into another wavelength, infrared light. If we want to see the earliest objects in the universe, we have to see that faint infrared glow. So why haven't we done this before? Well, we have. We launched the Spitzer Space Telescope, which isn't as well known as Hubble, but has made incredible discoveries of its own with the infrared capabilities Hubble lacks. But when it comes to resolution, Spitzer's images are a lot more like ground images,
than they are like Hubble images. To get Hubble quality images in infrared light, we need something more. We need a giant mirror. Spitzer's mirror is just over 2.5 feet across. Hubble's mirror is about 8 feet across, so that's about a bit taller than a human being. And Webb's mirror uses 18 hexagonal mirror segments to create a reflective surface more than 21 feet across, almost 2 stories tall. Clearly that's pretty big. How do we get something that size into space? Obviously we can't ship it like this. The answer is origami. We're going to fold Webb up inside the rocket that launches it into orbit. Once it's in space, it starts to unfold. The massive mirror opens up. Its tennis court-sized sun shield, which will protect it from unwanted infrared emissions from the sun, Earth, and Moon, stretches out. And all this happens while it travels approximately 1 million miles away, to a point farther away from our planet than even the Moon. So, what are we going to get for all this effort? We are going to be able to see past all these galaxies in the Hubble Ultra Deep Field. We're going to be able to see beyond even the most distant red dots in these images, the tiny, newly formed galaxies at the very edges of Hubble's vision. We're going to see the most distant and earliest galaxies in the universe, the first stars and galaxies to form after the Big Bang. We call these objects the universe's first light. Hubble has been able to observe the adult, teenage, and child galaxies of the universe. Webb will see the toddlers and infants, filling in our story of galaxy formation and evolution as surely as adding missing photos into a family album reveals how humans grow and change over time. But this isn't the only area where we know Webb will provide breakthroughs. This is Hubble's image of the Eagle Nebula, the famous Pillars of Creation photo. Inside these pillars of gas and dust, new stars are forming, but we can't see them because the dust blocks visible light. But it doesn't block infrared anywhere near as well. Infrared light can beam through the nebula, and if we can see it, we can see the newly formed stars within. Hubble's view of the Orion Nebula shows hundreds of newborn stars only a couple million years old. But if we zoom in on Spitzer's infrared image, we see thousands more hidden inside. Orion is the place where we get the best view of not just star formation, but also of the new solar systems forming around those stars. We know that planets, new Earths, new Saturns, new Jupiters are forming inside these dark dust rings, what we call interplanetary disks. But we can't see them. They are hidden behind the dust. Webb's infrared vision will allow us to see through these opaque clouds so we can discover how solar systems like our own came into being. We will be able to see what our own solar system would have looked like after the sun had formed, but before Earth existed. And Webb's vision is going to take us even farther than that, to individual planets beyond our solar system. This isn't one of Hubble's most dazzling images, but it is an important one. Several planets are orbiting around this star, but their light is lost in the bright glare of their sun. If we can remove the star's light, we can see the planets, these bright dots you see here. This is an infrared observation. Planets which don't shine with their own visible light are usually brightest in infrared. The best way to observe planets is with a high-resolution infrared space telescope. But Webb will be able to take even that another step further. Some extrasolar planets, from our point of view, pass in front of their stars. When that happens, some of the star's light passes through the planet's atmosphere. We can analyze that light and measure things about the atmosphere of that distant world. So what does that mean for us? Well, here is the plotted infrared light of 3 different planets. You're seeing the differences in those planets that indicate the presence of carbon dioxide, ozone, and water. These are the telltale differences between Venus, Mars, and Earth. The first signs of life elsewhere in the universe will not be photographs of civilizations or a visit by little green men. It will be features in the atmospheric spectrum of an extrasolar planet that show biological activity. And that's what Webb has the potential to give us, that tremendously exciting discovery. So when is all this going to happen? Webb is scheduled to launch in 2018, just 6 years away. An enormous amount of the work on the telescope has already been completed. All of Webb's 18 mirror segments have been ground, polished, coated, and tested. Its cameras and other instruments are nearing completion or in their final stages. But since Webb will be located 1 million miles away, it has to be perfect before it launches. So we're testing everything. The pieces get tested separately, then together, then as part of the actual telescope. They're tested to make sure they work in the extremes of space and that they can survive the violence of launch. When it's time to test them as part of the entire telescope, they're brought to NASA's largest test chamber, this cavern-like thermal vacuum chamber at Johnson Space Center, which is being refitted especially for Webb. If it looks familiar, that's because it's famous for being used to test the Apollo space vehicles. It seems fitting that that chamber, used to prepare humanity for its first true exposure to the heavens, is also where NASA's next great space observatory is coming together. Every decade, astronomers conduct a survey to determine the astronomy community's top priorities. Webb is their #1 priority. This is the observatory they want above everything else. We've already explored some of the reasons why, but not the most important reason. If Hubble is any guide, Webb's most important contributions to our understanding of the universe will probably surprise us. Because it was designed as a general-purpose observatory, it is extremely versatile. The Webb Space Telescope will be able to answer the questions we have, and then move on to questions that we haven't yet thought to ask. For example, before Hubble, we thought the expansion of the universe was slowing down. But Hubble made crucial discoveries to confirm that actually it's speeding up, and for that to happen, there may exist some form of strange dark energy. This discovery won its scientists the Nobel Prize in Physics this year. The universe doesn't always work the way we think it does. It surprises us again and again. We've only begun to chip away at the mysteries that are out there. And Webb, because it's designed for this purpose, will be able to explore, confirm, or deny these discoveries as they arise. And that is the true power of Webb. Its potential for unbounded discovery, its ability to reveal wonders we didn't even know existed. That capability, perhaps more than anything else, makes Webb the future of space astronomy.